All right, so the plan for today is just to continue with chapter 4, keep working our way through that because we probably won't finish 4.4 today. I've moved the deadline for the 4.4 homework 1 week, so that'll be due on Sunday the 9th instead of this Sunday. It's hard to believe that it's already going to be March this weekend. Um, so that 4.4 homework I kicked back a week, but the 4.2 multiplication rule section I think is still due uh, this week, and I think that's the only section that's due. But so I moved 4.4 back, but all of the other homework that was originally due this weekend still will be due. Just a reminder that the uh, Unit 1 exam is this week. So I did get an email about this. So when I'm doing these recordings, this is for the Zoom section that I'm teaching this semester. I also am teaching an online section, and I post the Zoom recordings to YouTube, and the online folks can watch them as well. But so any of this administrative material that I discuss here is in reference to the Zoom section, which is the meeting that we're in now. The online section has a different schedule. Um, but the Unit 1 exam for the Zoom section is this week. We've discussed the details, but a couple of things to note. Uh, I posted a chapters 4 and 5 subfolder in the supplemental materials folder as well. I guess that doesn't really relate to the exam, but that just goes with the material that was posted there, along with things like the formula sheet and the chapter 4 PowerPoints and so on. And really the biggest thing is um, just remember that there are no due date extensions on the exams. So make sure to build yourself in some margin. Plan to take the exam on or before Thursday night. That way, if anything happens, if there is a power failure, if you have a tech issue, you have time to kind of let that work out, to contact me, to get in touch with tech support, or to find another option, right? If it's Friday afternoon and your power's out of your house or something, you can go to a library, you can go to a CCAC campus. If it's Sunday at 10 p.m., your options are pretty limited. So build in some margin. I know that some folks like to take those, every spare minute to study for the exam, to prep for it, but I think the cost benefit there is really not in your favor. Taking another couple of days uh, to study for an exam, and then kind of rolling the dice that something might happen and you end up not being able to take the exam at all, of course, would be a much worse outcome. Okay, and the quote of the day today, this is something that one of my wife's colleagues would say, that velocity is a vector quantity. And what's meant by that is when we talk about velocity, a lot of times people use the word velocity interchangeably with speed, but really, if we're speaking technically, velocity consists of both speed and direction. So, you can be going a speed 10 miles an hour, but in what direction? If you couple a speed with a direction, I'm going 10 miles an hour in the direction, say, due east, that would be a velocity. Um, so velocity is a vector quantity. And what did she mean by that? So what she meant by that, whenever she would say that, is that, you know, different people have different tendencies, but some people have this idea that, like, okay, I want to accomplish some goal. I just got to get started, right? I just got to get something done, just get moving. In other words, like looking down at your feet and just making sure that your feet are moving, and you're like, okay, I'm making progress, but you might be headed in the wrong direction. So just doing something without a direction in mind is probably not going to get you where you want to go. But on the other hand, if we never look down at our feet and we're always just, looking at our compass and pointing in the right direction, and we never actually take a step forward, we also don't get where we want to go. So there has to be uh, a due respect for both sides of this coin. Some people are the kind of people who don't worry too much about the direction and just kind of jump into things. I tend to be kind of on the other side, the perfectionist procrastination side, where I'll spend, hours and hours pointing myself in just the right direction and never take a step forward. But if you're on either of those extremes, it's good to recognize when you're falling into that trap. And in my case, it's like, okay, this might not be a perfect product, but I need to just take a step forward at this point. I've gotten myself pointed in kind of a close enough direction. Now I just need to get going. Or the person who tends to just jump in head first without much thought maybe needs to, when they see themselves doing that, step back and say, okay, let me just take 15 minutes, schedule 15 minutes and say, let me make a plan. Let me make an outline. Let me point myself in the right direction. Maybe, maybe I'm off by a few degrees, but at least I'm not going 180 degrees from where I want to go. And kind of the way that I think of this is that effectiveness, so your ability to accomplish a goal, let's say, is something like efficiency times effort. So effort is like the speed, so to speak. It's, how many hours do you spend actually doing the task, actually working on it? And efficiency is the direction, it's the plan. How many hours do you spend planning how you're gonna use that effort? So if you want to learn the piano, learn to play the piano, well, you can spend a lot of time watching YouTube videos or reading books about what's the best method for learning the piano. Or you can spend a whole lot of time just sitting down and banging away on keys without much direction. Either one of those extremes probably isn't going to make you a very good piano player. Although I should admit that sitting down and banging on the keys might eventually make you a good piano player, while sitting there and watching thousands of hours of YouTube content on how best to learn the piano will certainly not make you a good piano player. So there is something to be said that, in a sense, effort outweighs efficiency, but really it's kind of your optimum here is a combination of the two. Right. So we have an exam coming up. Take some time to write out an outline, to plan what you're studying for the exam looks like. Maybe this would have been a better piece of advice last week, but so take some time to plan your study plan for the exam, but don't take so much time planning how to study that you don't actually get around to studying. And vice versa, don't just sit down and randomly start studying things without making a plan. Maybe that effort will be somewhat fruitful, but you can magnify how fruitful that effort will be with a little bit of extra planning. And then I think layered on top of this, so this is kind of an instrumental goals idea. Like, if I have a goal, how do I effectively achieve that goal? And then there's kind of the question of like, well, what goal should I shoot for? And speaking in terms mainly of career here, that impact, this, was kind of a buzzword a couple years ago, maybe not so much anymore, is something like effectiveness times relevance. So your ability to achieve a goal, kind of multiplied by how much your employer cares about that goal. If you get really good at playing the piano and you're an engineer, you put that on your resume and your boss is like, hey, why should I give you a raise this year? Or what was your performance like this year? And you're like, I got really good at the piano. That's cool. That was a high degree of effectiveness, but your boss doesn't care about it. So, always taking into account relevance as well. Of course, we're talking about if you're looking at say improving career or something like that. Um, I'm not saying that everything that you do should be geared toward that. So if you just want to learn the piano because that's something that you want to do, go for it. But if your goal is what can I do to push my career forward, also ask, what are the set of things that my employer finds relevant? What has a moderate to high degree of relevance for my employer? If I can get even moderately effective at those things, that's going to be a much bigger impact to my corporation than becoming highly effective, highly competent at things my employer doesn't really care about. So that was one of the buzzwords, is you want to have an outsized impact. I think that's kind of gone by the wayside a little bit, right? These buzzwords sound really good for a year or so, and then they start to sound like buzzwords and people start laughing at them. So, but I think there is a valid idea behind that. All right. So that's our prep material for today. And our goal for today is just to continue on with the PowerPoints in chapter 4. So here we're in the part 2 of 3. So there are 3 PowerPoints, again, posted on Blackboard. These have been up for a while, so I suspect that you already have these downloaded. Um, and we had worked through the first half or so of this part 2, chapter 4 PowerPoint, and we're just going to continue on from there. So just recall that we had a multiplication rule for independent events, and recall that we say that 2 events are independent if the knowledge that one occurs or does not occur does not affect the other one from occurring, does not affect the likelihood of the other one occurring. So for example, consecutive flips of a coin, we would think of as independent events, but maybe something like, oh, my PowerPoint is being a little wonky today. There we go. But maybe something like rolling a die, seeing what number comes up, and then rolling a die again and trying to get a number greater than the first number. Well, of course, those are dependent events because the higher the number on the first roll, the harder it is to get a higher number still on the second roll. Okay, so let's take a look at an example here. Suppose that we know from experience that a hard drive has a 2% chance of failing in any given year. So we choose to back up our data onto an independent hard drive. So we're assuming independence here. And the question is, what's the probability that both drives fail in a year? So the probability both fail, well, that's really the probability the first one fails and the second one fails. This is really a compound event. And the 2 hard drives failures are independent by assumption. So that's the probability the first one fails times the probability the second one fails, or that's 0.02 times 0.02, or 1/50th times 1/50th, however you like to think about it. That's 1 in 2,500, or 0.0004. So by having 2 hard drives, one that's backing up the other one, I go from a basically 1 in 50 chance or a 2% chance of losing my data to maybe a 4 parts in 10,000 or 1 in 2,500 chance of losing my data. I basically just square the probability of losing my data. And when a number is small, its square is smaller. Now we might look at this and say, well, in reality, are 2 hard drives really ever independent in this situation? Well, certainly if I have, one hard drive in my computer and the other one in my desk drawer right under my computer, they probably aren't independent. If I get, a water leak or something that floods my office, it's probably going to hit both hard drives. Or if there's a fire or something, both will be affected. But even if I do something like, put one hard drive in the safe deposit box at the bank or something like that, if I go, you know, if I go really strongly into the trying to make them independent. I mean, they both have the same data on them, right? If it's something with the data that's fundamentally corrupt, if I downloaded a virus or there just something about the data is not cooperating with my hard drive, that could cause it to fail. So are 2 hard drives ever going to be actually independent in a scenario like this? Probably not. But could we take measures to make them independent enough? Yeah, probably so. Um, so my wife's mom, my mother-in-law, who we get along great, uh, she was a math teacher at high school in Kansas for a long time, um, and when she would back up her data onto a hard drive because she had student grades and all kinds of stuff that would be a huge pain if she lost. And this was, of course, before the days of the ubiquity of the cloud storage and all of that, right? So she would actually have her backup hard drive in the trunk of her car with the idea that, that kind of makes things about as independent as you can reasonably make them without going to some crazy level. Like, I mean, I guess you could put in a safe deposit box at the bank, but then access is really difficult, right? If you actually need to get to it, or if you do that, you're going to be unlikely to actually back up your data as often. So there's a trade-off there between how safe something can be and how easy it is to access. That's also just kind of a general trade-off that we make, right? The more robust your security system for your house or car or whatever, often the more of a pain it is for the legitimate user or users to access. So there's always a trade-off between security like that, and if you go too far into the security side, if you make things too secure and then they're too difficult for people to use, then people either just don't use that security at all and it becomes overall less secure, or they find little shortcuts around, right? So people will like write down their password on a piece of paper and slide it under their keyboard or something if you make the passwords too hard to remember. Um, and then you just decrease security because now everybody's password is written down somewhere on their desk or something. Um, so there's kind of there's like a local optimum there with security. Okay, so let's take a look at this example. This is kind of it's somewhat of a toy example. So I know some of you are going into medicine or kind of science or nursing, things like that. So don't read too deeply into this example, but I think it's a good demonstration. So let's suppose we're testing for a certain disease in a clinical laboratory setting. And one way that we might be able to save some money, or maybe back in COVID, one of the issues was actually saving resources. Can we save reagents? Can we save the chemicals that are used to perform these tests? Or resources like tech time, lab techs, uh, when some of them were sick and so on, there weren't a lot of lab techs and there was a huge demand for running samples. Um, can we make better use of our tech time, for instance? So they might look at the ability to combine samples instead of running, one test for each individual patient. Maybe if we combine a bunch of the patients together and run one test on the pooled sample, maybe that could be helpful. Maybe that could save us some money or reagents or whatever it is that we're looking to save. Now, if I'm imagining something like I'm curious whether, any of the people in this, say, pool of 10 patients is positive for COVID, well, that's kind of a positive negative, right? So this wouldn't work if I was like, I had 10 people and I want to know what their glucose level is. Like everybody's got some glucose in their blood. And if I pull them all together, now I can't tell who has high glucose or low or moderate or whatever. Um, but if I'm looking to see, do any of these people have, evidence of COVID in their blood? Maybe we're looking for DNA or RNA that's unique to COVID, or maybe we're looking um, for antibodies or something like that. Uh, well, that's just a binary yes, no. The person is positive for COVID or negative. And if my test is sensitive enough, if it's able to pick up a low enough signal, I could pull together 10 patients and ask, is that pool positive? Is there any evidence of COVID in that pool at all? And again, provided that the biochemistry and all that, I guess, I don't know if it's chemistry or biochemistry, but provided that the chemistry works out properly, um, and that our instruments are sensitive enough and so on, uh, we might be able to pull together, say, 10 people's samples, run one test on those 10 people, and if the test comes back negative, then I can conclude that all 10 folks are negative. None of the 10 folks have COVID. Now, the downside is if the sample comes back positive, that means at least one of the 10 people is positive for, say, COVID. Um, so then I have to do something else. Then I don't know which one or two or three of the people were positive. So then I'd have to do follow-up testing. So that's certainly a downside. For a negative test is very nice. For a positive pool, um, at the very least, turnaround time is going to be longer. Um, and at worst, maybe it ends up actually even costing me more money. So if this was a disease that I think has a high degree of prevalence in the population, if I think that 90% of people are positive, I'm probably not going to pull samples at all. But even at the height of COVID, at any given point in time, not very many people had COVID. Not a high proportion of people had COVID. Um, that's not the, I'm not, you know, I'm not, whatever, making any kind of a general statement here, but it's just, numbers wise, at any particular day, maybe a couple percent of the population or something at most had COVID. So let's say that the probability that a patient has whatever disease we're looking at is 1 in 1,000. So it has a relatively low degree of prevalence in the population. And because of this, I'm interested in pooling samples. I think, okay, if one patient is unlikely to have the disease, then probably a pooled sample of 10 patients is also unlikely to have the disease. So a lot of times I could take pools of samples of 10 patients, the pool will test negative, and then I can just say with one test, all 10 of these folks are negative. So what's the probability that such a pool will test negative versus positive? Let's take a look at that. So let's look at a pool of 10 people. So we want to know what's the probability that the pool is positive. Well, note that that is the probability that at least one patient is positive. If I think of there being 10 patients, and I label them, say, patient 1, patient 2 through patient 10, there are a lot of ways that at least one patient can be positive. Maybe patient 1 is positive, everybody else is negative. Maybe patients 2, 4, and 6 are positive, everybody else is negative. Maybe all 10 patients are positive. I really don't want to deal with all of those different scenarios. But I realized that I could write this probability as 1 minus this the complementary event, which is the probability that no patients are positive or all patients are negative, that all patients do not have the disease. And I think I need to go one more click. There we go. We are assuming independence here between patients. But all patients being negative means, for instance, that, say, patient 1 is negative and patient 2 is negative, and so on, and patient 10 is negative. But we assumed the independence between the patients. Again, is this a reasonable assumption to make? Well, it depends on context. If I got a bunch of samples all from the same hospital ward, and probably not a very good assumption to make. If I got a bunch of samples from just generally around the community that came in, probably a much better assumption to make. But here, nevertheless, we're assuming independence for the sake of this calculation. This is 1 minus the probability that an individual patient is negative to the 10th power. Right, our multiplication rule for independent events, roughly speaking, just means each of these ands turns into multiplications. So probability that patient 1 is negative times probability patient 2 is negative times probability patient 3 is negative, and so on. But each of them has the same probability of being negative. Now we know the probability that they are positive is 1 in 1,000. That's the complement of being negative. Patient is either negative or positive for the disease. They either don't have it or they do have it. So we see that the probability of the pool is positive, the group of 10 is positive. In other words, the probability that at least one patient in the pool has the disease is 1 minus, parentheses, 1 minus probability that an individual is positive to the 10th power, to the number of patients in the pool. This structure here is actually kind of a common structure in probability. This like 1 minus parentheses, 1 minus something to a power. This comes up every once in a while. Now, if we bring up the calculator here, if we go over to the calculator and plug in some numbers, so what's 1 minus probability of positive? Probability of positive was 1 in 1,000. So 1 minus 1 in 1,000 is 999 over 1,000. And let's be careful with our order of operations here. I got 1 minus parentheses 999 out of 1,000. And then to the power, using the caret symbol above the divided by sign, to the power 10. And I see I get 0.009955. Or that's about, well, if I round to say the nearest percentage point, that would be about 1%. So if I pull together 10 patient samples, there's about, with a disease with a prevalence of 1 in 1,000 in the community, there's about a 1% chance that uh, that pool will test positive, or about a 99% chance that it will test negative. So I could imagine, for instance, that 99 times, let's say that I have 100 pools of 10 each, so that's 1,000 people. About 99 times, those pools will test negative, and I can conclude that that everybody in the pool is negative and doesn't have the disease. So I'd have to perform 99 tests there. And then one test will be positive on average. One pool will be positive. And then maybe I just have to go and just test each of those individual 10 people separately to figure out which one, or perhaps two or three or something, are positive. So that would be one test for the pool and then 10 more for the individuals. So I'd have like 99 tests plus one plus 10. I could get away with 110 tests instead of, for 1,000 people, if I had tested each person individually, I'd had to do 1,000 tests. I could get away with about 10% the amount of reagents, and probably not quite that much savings in tech time, because there are some things that techs are going to have to do for every patient anyway. But I could get away with a substantial savings in resources. And at a time when resources were pretty scarce, that might have been a pretty significant savings, a pretty meaningful savings. Now, I might ask myself, well, if pulling 10 people is better than testing each person individually, or essentially just doing pools of one person, uh, well, what if I pull 100 people? Is that going to be even more better, right? What if I pulled 100 patients at a time instead? Well, what would a pool of 100 patients look like? What would change? Well, this is still our question. That's still the same. That's still the same. Here I just have 100 people who all have to be negative for the whole pool to be negative. Again, we're making a huge assumption here that our uh, our machinery and the chemistry and all of that is sensitive enough, especially when we start diluting things by 2 orders of magnitude. That's probably pretty questionable at this point. So we're really in the realm of math here, rather than what might actually happen in a laboratory setting. Maybe a pool of 10 or 20 would work. I kind of doubt that a pool of 100 would work, but we'll just kind of pretend that it would, that our instruments are sensitive enough. So this 10 going to 100 means this exponent goes to 100, as does this one, as does this one. And one little calculator trick, if I do second and then the negative sign down here next to enter, see the yellow above it is ANS, answer. Or actually, I don't want the previous answer. I want the previous entry. Second enter. There we go. Brings up the previous entry. So I don't have to type it in again. I just need to change the exponent of 10 to 100. So second enter brings up the previous entry. I have the same formula, but with just 100 replacing 10. And I see I get 0.095, or about 9.5%. So if I pull together 100 folks in a pool, and on the caveat that if all of the chemistry and instruments and so on were sensitive enough, I would get 9.5% chance that my pool ended up positive. So I'd have to run 10 pools of size 100 to kind of sample 1,000 people. Only 9.5% chance the pool is going to come up positive. So kind of on average, out of 10 pools, 9 of them would come up negative. So I do 9 tests to eliminate 900 people from consideration of being positive. And then for that, last pool of 100 that came up positive, say on average, one of them will come up positive. That one, maybe I'll test everybody in the pool, and that'll be 100 more tests. So I didn't really save all that much. I still have about 110 tests that I have to perform. I get a little bit of an advantage from this being 9.5% instead of actually 10%, but that's not too huge of an advantage. So a couple things to think about here. A couple little notes. One note is directly related to the probability we're discussing. And that's that, well, I think most people, if they looked at this and were asked this question, I think their answer would be something like, well, I have 10 patients, let's say the pool of 10. I have 10 patients, each of which has chance 1 in 1,000 of being positive. So that should be 10 in 1,000, or 10 times 1 in 1,000. That's 1 in 100. That's exactly 1% chance of the pool being positive. Or if we ask them about the pool of 100 patients, I think they would say, well, that's 100 people, each of which has 1 in 1,000 chance of being positive. So that's 100 over 1,000, or 1 in 10, exactly 10% chance of a pool being positive. Note that our 1% estimate is kind of concordant with the actual math that we did, but it is an estimate. This was the actual answer we got for a pool of 10. It wasn't exactly 1%. We had to do this 1 minus something to the 10th power to get the right answer. But it turned out that in this scenario, our kind of naive guess would have been pretty close to the right answer. However, here, 9.5% versus 10%, that's a half a percentage point off. And especially on a scale of 10 percentage points, that's like a 5% relative error. Being 5% off isn't too great. And if we had picked even a larger number for the pool, we'd have had even a larger error. So our kind of naive guess really turns out to be an okay approximation under some certain assumptions, but a poor approximation under other assumptions. So we don't want to just go this route. We want to actually do the math. We want to actually do the algebraic steps that are supported by our probability theory that we've discussed throughout chapter 4. Right. So we really do have to follow the rules and the theorems and the different laws that we've set forth, the addition rule, the multiplication rule, things like that. So we don't have a rule that says, number of people times probability gives me the probability a pool is positive. The second note is a little more related to the scenario here. And I think we have people who are interested in like computer science and programming, that kind of thing. So note 2 is related to this. So I have a pool, let's say of size 100, and let's say that my pool tests positive. So most of my pools test negative, and I can just from that conclude that everybody in each pool is negative when the whole pool tests negative, again, under our assumptions that things are sensitive enough and so on. But when my pool tests positive, one approach is to say, okay, just then sample every single one of these 100 people and figure out who the positive one is, or the positive two or three, or figure out who the positive folks are that way. But we know that if we have 100 people who test positive, it's actually a pretty good chance that there's actually only one positive person in that 100 people. The chance that any one person is positive is 1 in 1,000. And if I have 100 of those people, I mean, if I have 1,000 of them, I'd expect on average one to be positive. If I have 100, I'd expect on average none to be positive, except for the information that I have that the pool is positive. So at least one person is. It's probably quite likely that one individual in this pool is positive and 99 are negative. So if I was very, very concerned with saving as much resources as I could test each of these 100 people individually right now, but is there a better way to search for this? Let's suppose that there's just one positive person. Give me 1 second here to pull up a different screen. I kind of just realized that I closed it as I was closing my windows at the start of class. Okay, so in the supplemental materials folder, there's a little, oh, let me get my Zoom thing back up here. There's too many screens and windows to mess with today. There we go. In the supplemental materials folder, there is a little picture, supplemental materials, chapters 4 and 5 folder, and it's called the coin balance problem. And here's an interesting little question. I actually really like this question. This was from an app called Brilliant. And this was several years ago that I encountered this, but I saved it, and I sometimes use it as an example in stats whenever I know that there are quite a few folks in kind of the computer science realm. And here's the question. I promise it does actually tie into what we're discussing here. So you have 25 coins. There's exactly one fake coin, which is lighter than each of the others, and each of the others have equal weight. Using only a balance scale where you can put, some stuff on one side, some stuff on the other side, and the heavier side will go down. What's the fewest number of weighings you would need to make to ensure that you can determine the fake coin? So a balance scale, if both sides have the same weight, it stays flat. If there's a heavier side, that side goes down. So this is kind of an interesting question. Let's think about this for a minute over here. And I think we can maybe see already the relationship to this. We're looking for the one positive patient in amongst this 100. We're kind of presuming that there's only one. Or we're looking for the one fake coin amongst these 25 coins. So let's think about the coin problem. We have 25 coins, and exactly one of them is fake. So what's the most number of weighings or what's the fewest number of weighings I need to ensure that I found the fake coin? What's kind of my like best worst case? What's the best I can do as a worst case scenario? I could weigh the coins one at a time. I could take, coin 1 versus coin 2. If they weigh the same, if it balances, then I could get rid of coin 2 and put coin 3 on there. If that balances, get rid of coin 3 and put coin 4. And worst case scenario is that coin 25 is the fake coin. So I could weigh one at a time. And this would take 24 weighings. So I know that I could get it done in 24 weighings. Can I do better than that? We probably see a way to do better than that pretty much right away. Instead of using coin number 1 as my reference, I could weigh like 1 against 2. If they balance, I know that neither of those two are the fake coin. Then I could weigh 3 against 4, and so on out to worst case would be 23 weighed against 24, and they would all balance. And then that would mean that 25 has to be the fake coin if everything else balanced. I wouldn't even need to put it on the balance. So this would require 12 weighings. Well, maybe put a double underline under that. So I could do it in 12 weighings. Can I do better than that? Does anybody have a thought? Any of my, particularly my computer science folks, might have encountered something like this before. Anybody have a thought on how I could do better? Well, one thing I can maybe do is I could take stacks of coins. I could take like coins 1 through 12 on one side and weigh those against, say, coins 13 through 24, leaving 25 off here to the side. If the 1 through 12 balances with the 13 through 24, none of those stacks, neither of those stacks can include the fake coin. This must be it. So kind of the worst case would be that one of these stacks is heavier, or whichever way it is lighter. Let's suppose that we determine that the stack 1 through 12 contains the fake coin. So we've done one weighing at this point. And I could do the same thing with 1 through 12. I could do 1 through 6, weighed against 7 through 12. That's a second weighing. And maybe let's just say we determine that 1 through 6 contains the fake coin. I could do 1 through 3, weighed against 4 through 6. That's a third weighing. And maybe let's say we determine that 1 through 3 has the fake coin. Well, here I have 3 coins, so what could I do? I can't split them evenly anymore, but I have 3 coins. That means maybe I can weigh coin 1 against coin 2 and leave 3 off to the side. If coin 1 and coin 2 balance, 3 has to be the fake coin. If coin 1 and coin 2 don't balance, then I've identified the fake coin. So with a fourth weighing, I've identified the fake coin. So this is called a binary search. And I can, using a binary search, find the fake coin in 4 weighings. And something, I really love how this problem is devised, because something that you might notice is, wait, I did a binary search, I can do it in 4 coins, but if you enter the answer 4 into the system, it's going to tell you it's wrong. You can actually do a little better. Why is that? Well, it actually leads you to the better solution, this problem, the way this was constructed. In fact, if I thought of binary search and went through that math and said, okay, it works this way, the last step here really makes us realize that we can make use of the stack that we're leaving off. In other words, what I could do is I could start with 25 coins and break it roughly into thirds. In other words, I could weigh, say, 1 through 8, 9 through 16. I could weigh those against one another, and I could leave 17 through 25 off. If one of these is heavier than the other, then I've cut my search space down to 8 coins. If these balance, then my search space is this remaining 9 coins. So worst case scenario, let's say that 1 through 8 balances with 9 through 16, and we're left with 9 coins to look through. I can do the same thing here. I'm going to rename these 1 through 9. So I have coins 1 through 3 balanced against 4 through 6, and then leave 7 through 9, that stack off. And let's say we identify that 1 through 3 contains the fake coin. I can weigh 1 against 2, leave 3 off. I can do it in 1, 2, 3 weighings. So I actually can do a ternary search and get it done in 3 weighings. I thought this was a really nicely constructed problem. And also it has something to say about this, right? So when I have a positive result, if I really, really, really want to make the most efficient use of my resources, I could actually split to like a pool of 50 and 50. If there's only one positive, if that's the case, then exactly one of these will be positive and the other one negative. I can split this 50 into say 25 and 25 or something like that. Or maybe I could even split this 100. I could go even a little further than a binary search. I could split it into maybe 10 pools of 10, right? So I have lots of different choices here, but the point is that I could pretty efficiently, if I did say 50 versus 50, so this would be one test that I have to run, two more for each of these pools, 25 versus 25, two more for each of these pools. Let's say this pool tested negative. I could do a binary search like this. I would have to do 9 tests for the 900 patients in pools that tested negative, and then a handful more, maybe like 10 or 15 more. I could do like 25 or 30 tests to find the one positive in the 1,000 people. Instead of having to do 1,000 tests, I can cut my reagent use by maybe a factor of 30. Now, of course, there are all kinds of trade-offs here. Nobody's going to do a complete binary search like this, even if they are really worried about reagents, the complexity, the chance of making an error, the just the turnaround time. I mean, you can't say, okay, we'll have the answer back to you in 2 weeks. So all of those constraints come into play as well, right? But just showing how this probability here, these probabilities could lead to, at least mathematically speaking, the ability to pool people and get really huge advantages out of being able to pool people. We can take our search effort from linear, from one amount of effort per person tested, to logarithmic. And that's really a huge benefit. Okay, so let's look at dependent events now. So dependent events are events that are pairs of events that are not independent. In other words, if I have two events A and B, and the knowledge that A has or has not occurred affects my estimate of the likelihood of B occurring, those would be dependent events. So one thing that we might not really think of as a dependent event, but if we think a little harder, we realize it is actually drawing two cards from a deck of cards without replacing it. Like when I'm drawing a poker hand, right? I pick the first card and then I pick a second card from the deck. Those are not independent events. Since I didn't replace that first card, if I draw a card and I get the king of clubs, well, certainly I cannot draw the king of clubs anymore on the second draw. I didn't put it back. That's not in there anymore. But even at that, what is the probability of an ace of spades? Well, on the first draw, it was 1 in 52. But after I draw a king of clubs, there's one ace of spades left in there and only 51 cards left over. So 1 in 52 chance for the first draw. If I draw the king of clubs, probability of an ace of spades goes up to 1 in 51 chance. The number of cards in the sample space, so to speak, for the second draw is only 51. It goes down one. So if we draw cards from a deck without replacing them, those would be dependent events. The card we draw on draw 1 or 2 or 3. If we draw cards from a deck and we do replace them, if I draw the king of clubs, write down on a note somewhere I drew the king of clubs, put it back in, shuffle the deck, and then draw another one, those would be independent events because we have exactly the same setup the second time as the first time or the third time or whatever. So if we draw with replacement, we draw, look at it, write it down or something, put it back in, consecutive draws would be independent events in that case. But if we draw without replacement, draw it, keep it in our hand, and then draw another one, those would be dependent events. So there's some subtlety here. Another example is something like IQ and annual salary. These kind of correlate reasonably well, except that, typically folks with really high IQs don't have all that great annual salaries. So you might say, oh, well, these aren't really dependent events because, if I know somebody's IQ, I can't definitively determine their annual salary. But that's not really what dependence is looking at. It's saying if I know something about their IQ, can I make a different estimate of their annual salary? And we probably could, right? Um, so, lots of bright folks end up being like authors or something like that, and or maybe musicians because they just like pursuing those kind of fields, or maybe like philosophers, right? And that's usually not going to make you as much money as going into sales or going into business or something like that. Or something like a person's age and the volatility of their investment portfolio. As people get older, they tend to opt for safer investments. When you're in retirement, you're more concerned with having stability of your investments so that you can draw from it kind of dependably year over year. But when you're younger, you're not really looking at drawing from it anytime soon. You can tolerate a little more volatility. Now, does that mean that every older person has a low volatility portfolio or every young person has an aggressive portfolio? Well, no, of course not. But there's certainly a dependence here. The probability somebody has a high volatility portfolio if they're over the age of 60 is probably much lower than if they're, say, in their 20s or 30s. Uh, this almost goes without saying, but we really ought to make the point that since dependent events are not independent, we can't use the multiplication rule for independent events. We can't use that nice special case. So to build up a multiplication rule for dependent events, we need one more idea. This idea can be kind of complex, the idea of conditional probability. There's quite a bit that can be said on this, and I might actually post a supplemental like YouTube video there's a couple of good YouTubers that I've seen post kind of, little short videos, not shorts, not like 40 seconds, but shorter videos on this, 10 minutes or 15 minutes or something. So maybe I'll try to grab one of those and post it just as a little bit of extra information on this. But the conditional probability, it's denoted probability of, and what goes inside of the probability operator is an event, and the event is this event. B vertical line, A. This is not division. A lot of people want to make this division. They want to make this like probability of B divided by probability of A. That's not what we're saying. This is a special notation for an event. And this thing, B vertical line A, that whole thing, the way we verbalize that is we say B given A. In other words, probability of B given A is our estimate of the likelihood that event B will occur given the knowledge that A has occurred, right? It's like our estimate of the likelihood that it will snow outside today, given that we know that it's less than 20 degrees today, right? It's the probability of B occurring given that A has occurred. Now note that if A and B are independent, then probability of B given A, well, B's probability is not affected in any way uh, by the occurrence or non-occurrence of A. So then probability of B given A is just probability of B if A and B are independent. But if they're dependent, in general, if they're dependent, this is going to not be the same thing as probability of B. So if I ask just as a general question, what's the probability it snows outside today? And I don't know what day of the year we're talking about. So on a given day, what's the probability it snows outside? You might say, I don't know, 10% or something. And then I say, well, what's the probability it snows outside given that it's less than 20 degrees outside? You say, oh, okay, well, less than 20 degrees places me kind of in winter. So maybe that probability goes up to 15 or 20%. So probability of B given A, we can think of it a couple different ways, just like any of these probability statements. We're mostly going to think about it mathematically at this point. We can think of it kind of as frequentists. We can say, okay, on 100, say, similar days where event A has occurred when it was, say, less than 20 degrees outside, on how many of those days did it snow? Where probability of B just says, just on 100 days, how many of those days did it snow? Probability of B given A says, find me 100 days where it was less than 20 degrees outside on that day. And of those days, of that subset of the population of all days, when we're looking at just those ones, say 100 of them where it was less than 20 degrees, how many of those did it snow on that day? And then there's kind of the Bayesian way to look at it is I have some degree of belief that it will snow on a given day. Maybe like I'm not going to go on a long road trip if I think it's going to snow that day. And my degree of belief is probably going to increase if I know that it's cold outside that day. The chance that my, trip all around the city is going to get postponed to another day because I don't want to go when it's snowing. That chance, that belief is going to be higher than that I'm going to push my trip to another day if I know that it's less than 20 degrees that day. So a couple of different ways to think about how this could apply or what this means in the real world. But mathematically speaking, this idea of conditional probability is what we're going to look at next. We're going to look at the mathematics of it. We have a multiplication rule for independent events. So if A and B are independent, probability of A and B equals probability of A times probability of B. In other words, what I'm saying here is for the compound event A and B to occur, of course, A must occur and B must also occur. So A, did that occur or not? If I'm in the event, yes, that has to have occurred. And same with B for me to be in the event. How often does A occur? A occurs with probability of A. And then B also has to occur. So of the times that A occurs, of the times I can say, yes, event A happened, what proportion of those has probability B happened? Well, probability of A times probability of B. If A and B are dependent, again, we have probability of A and B. This compound event, A and B, means, again, if I say, if I'm in the event, has A occurred? Yes, A must have occurred. If I'm in the event, has B occurred? Yes, it also must have occurred for this event to have happened. Well, for event A to have occurred, how often does that happen? That happens with probability of A. But now given that I've said, yes, A has occurred, now what's my probability of B occurring? It's not just the overall probability of B anymore. It's now probability of B under the knowledge that A has occurred. If A didn't occur, I'm not in this event at all, and I don't really care whether B occurred or not. A and B failed. I'm not in that event if A did not occur, regardless of what happens with B. So to be in this event, A must occur. That happens with probability of A. And B must also occur given that A has occurred. That is this probability, B given A. That's the probability that B also occurs. And note that this is not just probability of B because the knowledge that A has occurred, the knowledge, for instance, that it's less than 20 degrees outside, affects my probability of B occurring. So I have to kind of account for that dependence between these two events, A and B. Since A and B must both occur for A and B to occur, well, I need A to occur. That's with probability of A. There are no conditions yet. But then I also need B to occur, given that I've already know that A has occurred. But A's occurrence affects B's likelihood of occurrence, so I need to be talking about probability of B given A here. And again, remember, if these were independent, probability of B given A is just the same as probability of B, because if they're independent, B doesn't really care what A does. So we see that really this is a special case, the multiplication rule for independent events, of the more general multiplication rule for dependent events. If A and B are independent, probability of B given A is just probability of B, and we get the special case, the independent event rule. But the more general rule is the dependent event rule with the conditional probability. Okay, let's look at an example. Suppose we run a manufacturing plant producing widgets. If you've never heard this word before, a widget is just like kind of like how in math we have a variable x that we use just to represent some number. A widget is like a business idea where it just represents something that we're manufacturing, whatever it may be. There are 4 machines producing widgets at the same rate. For a properly functioning machine, the probability of producing a bad widget is 4%. So even a properly functioning machine doesn't get it right all the time. But one of the machines is malfunctioning and it's producing all bad widgets. And we imagine that, our 4 machines are producing these widgets, the properly functioning machine, some bad ones, some good ones, the malfunctioning machine, all bad ones. They come off the assembly line, they get packaged up, they get, put in a warehouse somewhere. And then we want to do some quality control. So we randomly choose a widget from that warehouse where these are all jumbled up. The machine 1 or the machine 4 widgets, they're all jumbled up. And we randomly choose one. What's the probability that it's a bad widget? Well, there are 2 ways to get a bad widget. We can get a bad widget from a malfunctioning machine or bad widget from a properly functioning machine. Well, okay. So our event, bad widget, bad widget, which I'll just call bad, I can break that event into kind of 2 sub-events, bad and came from a properly functioning machine, or it's a bad widget and came from a malfunctioning machine. A widget, a specific widget could not have both come from a properly functioning machine and a malfunctioning machine. So these are mutually exclusive. These are mutually exclusive events. Because a given widget either came from a properly functioning machine or a malfunctioning machine, but it can't have come from both. Well, then the probability of a bad widget is the probability of a bad widget, a widget that is both bad and properly functioning and from a properly functioning machine, which we'll call a bad widget from a properly functioning machine, or a widget that's bad and from a malfunctioning machine, which we'll call a bad widget from a malfunctioning machine. Well, I have the probability of A or B, probability of A or B, where A and B are mutually exclusive. Well, wait, that's just our addition rule for mutually exclusive events. That's probably of a widget that is both bad and from a properly functioning machine, plus probability of a widget that is bad and from a malfunctioning machine. But now I can switch gears and use my multiplication rules. So if I look at this first probability here, for instance, I have probability of event one and event two, event one getting a bad widget, and event two getting a widget that came from a properly functioning machine. Are these independent? Does the likelihood of the widget being bad change depending on which kind of machine it came from? Well, certainly it does, right? If a bad widget, or sorry, if a widget came from a properly functioning machine, the probability it's bad is pretty low. If it came from a malfunctioning machine, it's 100%. So these are uh, the type of widget we get, bad or not bad, and the type of machine, properly functioning or malfunctioning, are dependent events. If I know the type of machine, that gives me a different insight into the likelihood of getting a bad widget and vice versa. So I use my multiplication rule for dependent events here. This is the probability. Well, how could I break this up? I guess I could do probability of getting a bad widget times probability of properly functioning machine given bad widget. Mathematically, I'm allowed to break it up this way. Is this helpful for me? Well, actually, probability of bad widget is the thing I'm looking for in the first place. I don't think this actually really helps me. I could choose to break it up the other way, right? The event A and B is the same as the event B and A. I can just, choose which ordering works best for me. So instead of making the probability by itself, probability of bad widget, I'm going to make it probability of properly functioning machine. Well, that I know. I know that 3 of the 4 machines are properly functioning, producing bad widgets or producing widgets at the same rate. So the probability that a given widget comes from a properly functioning machine is 3/4. And then I have times probability that I get a bad widget given it came from a properly functioning machine. This I also know. Given a widget comes from a properly functioning machine, I know that the probability that it's a bad widget is 4%. And I can do something similar for this second one here, probability of malfunctioning machine. 1 in 4 widgets comes from the 1 out of the 4 machines that's malfunctioning that are producing widgets at equal rates, times probability of a bad widget given malfunctioning machine. So this is the background supporting what I have on this slide. And we can see from our first term here, the green one, that's 3/4. 3/4 of our widgets come from properly functioning machines times 4%, the probability of a bad widget given the widget came from a properly functioning machine, or that's 3/4 of 4% is 3 percentage points. And then what's the probability of bad widget and malfunctioning machine, the red part over here? That's 1/4 of the machines are malfunctioning, 1/4 of the widgets come from a malfunctioning machine, times, well, what's the probability of a bad widget given a malfunctioning machine? 100%. Malfunctioning machine produces just all bad widgets. 1/4 of 100% is 25 percentage points. And then using mutual exclusion and the addition rule, we can add these together to get 28%. So overall, when I go to my warehouse and I pull out a random widget that might have come from any of the machines, there's a 28% chance that I get a bad widget. Any questions so far? Okay, let's look at another example. So again, looking at the multiplication rule for dependent events, what's the probability that, say, on 2 consecutive draws from a deck of cards, without replacement, I draw a heart, then a spade. So I'm thinking of something like a poker hand, right? I draw my one card, and if it's a heart, then I draw a second card, and if it's a spade, then I'm in the event. If my first card is something other than a heart, I'm immediately not in the event, regardless of what the second card is. Or if I draw the first card and it's a heart, and it comes back to me and I draw the second card and it's anything other than a spade, I'm also not in the event. So what's probably I draw a heart, then a spade. In other words, heart on the first draw and spade on the second draw. The then is actually kind of important here because if it was just a heart and a spade on two draws, I could get a heart or a spade on the first draw and then the other one on the second draw. So that would be a bit more of a complicated scenario. But here, heart, then a spade. Heart on first draw and spade on second draw. Well, that's probability of drawing a heart on the first draw times probability of drawing a spade on the second draw, given that I drew a heart on the first draw. Well, what's the probability that I draw a heart? There are 13 hearts out of 52 cards. Or you can just think 1/4 of the cards initially are hearts, but I think it's in this scenario, it's better to think of each card individually because the second probability, we might think, oh, there's, okay, 13 spades out of 52 cards, but be careful. We drew a card in the first draw, did not replace it. So now there's only 51 cards left, 13 of which are spades. And of course, these are all equally likely. That's one of our assumptions for probability at this point. So in my first draw, there are 52 cards for me to draw from, 13 of which are hearts. My probability of drawing a heart is 13 out of 52. And then on my second draw, there are 51 cards for me to draw from, 13 of which are spades. So I draw another one, 13 out of 51 chance that I draw a spade on the second draw, given I drew a heart on the first draw. Or that product is about 6.37%. As a little side note, a little kind of technical detail, what if I'm playing with three other people? I'm playing a round of poker. I draw my first, let's just say I draw first. So there's 52 literal cards in the deck for me to choose from. I draw a card and it's a heart. Yay, I'm happy. I can still satisfy the event. The other three people draw a card and it comes back to me. Well, now 4 cards have been drawn from the deck. From the deck that I see in front of me that I can draw from, there's actually only 48 cards. Should I make the second probability here 13 out of 48 in that scenario? Does it matter how many people were sitting at the table with me? Well, the answer is basically no, because I don't know what any of their cards are, right? Presumably they're drawing their cards and keeping them hidden. So it's as if their cards were still in the deck. I can't actually physically draw, this person's card, but I have no idea what card they have. They might have a spade, it might be a heart, it might be a joker or something. Well, let's not say jokers because then there wouldn't be 52, but it might be any of the cards, right? The only thing that I know about their card is it's not the one in my hand, and that's also what I know about the cards that are left in the stacked up deck in the middle. So none of that really matters. So you might be thinking to yourself, well, why isn't this 48 or something if I'm playing with 3 other people, or if we're playing with a bunch of people? Why? Well, the reason is that I only have information about one card, the one card that's in my hand that's a heart. So it's 13 out of 51. Whether just doing this myself at a table, drawing cards for some reason, maybe I'm really bored, or whether I'm playing a poker game with 3 other people, 4 of us total, or whether I'm playing a game with 10 people or something, or doesn't matter, it's still 13 out of 51, because the only information that I have is about the one card that is in my hand. What's the probability of drawing 2 hearts on 2 draws without replacement? I have to get a heart on the first draw and a heart on the second draw. The heart on the first draw is the same as originally, 13 out of 52. And kind of as an aside, even if there were 4 people at the table and I was the last one to go, this wouldn't be like 13 out of 49 or something, because again, I don't know anything about the other people's cards. Still 13 out of 52 for the probability of drawing a heart in the first draw. But for the second draw, there are 51 cards to draw from, but I've actually kind of used up one of the hearts, right? It's in my hand. I can't, if I drew the ace of hearts on the first draw, I can't draw the ace of hearts in the second draw again. there's only 12 hearts left in the deck. It's a little harder for me. It's a little less likely for me to draw two hearts in a row than to draw, say, a heart then a spade. So 1350 seconds times 12 51st, about 5.88%, a little less likely. So you can imagine, if you know a bit about poker, like getting a flush, getting five cards that are all the same suit, that's kind of unlikely to happen because if I draw two hearts on the first two draws, then on the third draw, there are only 11 hearts left in that deck, and there are still, roughly speaking, 50 cards left in the deck. And then if I draw a third heart, there's only 10 hearts left in the deck now. Each time I successfully draw one of the same suit, I drop the number of that suit in the deck by one, making it harder to draw yet another card of the same suit. But if I was just trying to draw cards of a bunch of different suits, if I draw a heart, then there's a whole bunch of spades and clubs and diamonds still in there. So we can see that, drawing a flush is a pretty darn good poker hand because it's pretty unlikely. The way that poker hands are ranked, which ones beat other ones, are the less likely hand is ranked higher. The less likely hand beats the more likely hand. So like four of a kind beats three of a kind because it's harder to get four of a kind. It's less likely to get four of a kind than it is to get only three of a kind. Okay, let's look at this example problem. Suppose that we're playing kind of the world's most boring game show. And the way this game show works is we roll a six-sided die. If we get a one or two from the roll, we go over to box one and we draw a card from there. If we get a 3 through 6, we draw a card from box two. Box one has 60% good cards, 40% bad cards, 60%, we win a prize, 40% we win nothing, whatever. Box two has 10% good cards, 90% bad cards. What's our overall probability of getting a good card? It's not just going to be 60% or 10% because we get sent to box one or box two, some proportion of the time. One thing that we can, one schematic diagram that we can use to help us with these kind of calculations is called a tree diagram. So remember, for our addition rule, we kind of had this idea of a Venn diagram that helped us out. So just to kind of recap, the addition rule was related to A or B. And if our events were mutually exclusive, sharing no outcomes in common, then probability of A or B equals probability of A plus probability of B. So the or kind of turns into a plus, and we had Venn diagrams to help us here. Or if they were not mutually exclusive, there are some overlaps, there are some outcomes that are shared between the two events. And if I just look at probability of A plus probability of B, I've kind of double counted the folks who are in the intersection there. I've got to subtract off probability of A and B. So this Venn diagram was sometimes a helpful schematic. Multiplication rule dealt with A and B, that type of event. Probability of A and B equals probability of A times probability of B if independent, or probability of A and B equals probability of A times probability of B given A if not independent, if dependent. And for dependent events, I suppose we could use this for independent events, but I think it's most often used for dependent. we have tree diagrams. They can be a helpful schematic. They can just kind of help us to keep things sorted out and arranged to make it a little bit less confusing. Sometimes following the algebra alone can be a little hard to follow, but using a schematic like this can help us organize things a little bit. Okay, so this tree diagram, how does it work? We basically start on the leftmost side over here and we start branching. We say, what's the first, in a sense, kind of decision that I am faced with? Should I go to box one or should I go to box two? Well, I get sent to box one if I roll a one or a two on a fair six-sided die. That's 1/3 of the time. And I get sent to box two 2/3 of the time. If I get sent to box one, so given that I got sent to box one, then I could either get a good card or a bad card. That's another branching. Well, what's the probability that I get a good card given that I'm at box one? This is a conditional probability that's on this branch. It's conditioned on what happened on the previous branch, what branch this kind of sub branch is branching off of. The probability I get a good card and win the money, given that I'm at box one, is 60%. So the probability of a good card here is not 60%, but it's just the probability I get a good card given that I'm at box one. And the probability of getting a bad card and losing the game, given that I'm at box one, is 40%. And analogously for box two, 10% chance that I get a good card given that I'm at box two, and 90% getting a bad card given that I'm at box two. And I see there are two ways for me to get a good card, right? If I look at the far right section over here, the leaves of the tree, so to speak, there are two ways to get a good card. I could have gone to box one and gotten a good card, or I could have gone to box two and gotten a good card. Those are mutually exclusive. That or is mutually exclusive because I can't go to box one and box two simultaneously. So what's the probability I got a good card from box one? In other words, what is the probability I got sent to box one and got a good card? Well, that's probably I got sent to box one times probably I got a good card given I got sent to box one. Note that that is just the product of the probabilities along the branches. So to get to this top leaf here, this top good card, I had to go up, up, basically. And if I multiply those probabilities along that path, 1/3 times 60%, that's exactly what I get here, or 20 percentage points of contribution from the top good card. Or from the bottom good card, what's the probability I went to box two and got a good card? Oh, wrong way. That's down, up. And again, if I multiply the probabilities along that path, 2/3 times 10%, that gives me about 6.7 percentage points. And remember that or from all the way back here, I could get a good card. I could get sent to box one and get a good card, or I could get sent to box two and get a good card. Mutually exclusive. I can just add the probabilities together. 26.7%, a little more than a 1 in 4 chance of getting a good card overall in this game. Any questions on that? As a little side note, when I do a complicated calculation like this, it's good to check my answer. I got a number as my answer. I'm claiming it's a probability. Is it between 0 and 1? Yeah, it is. That's a good thing to check. It's between 0% and 100%. Is it kind of sensible? Like, best case scenario for me would be if I could cheat and like roll a one or a two every time and go to box one. Box one is certainly more favorable for me, right? Then if I could cheat and go to box one all the time, I would get 60% of the time I would get good cards. So I know that my real answer can't be more than 60%. And vice versa, if I like, if the game show host was cheating and had a loaded die and I could never get to box one, If they didn't want to pay me money and they always sent me to box two, the worst I could do is a 10% chance of getting a good card. So my end result should be between those two, right? The worst possible if I always got sent to box two versus the best possible if I always got to box one. And indeed, it is between 10 and 60%. So this seems reasonable. In a lot of these application problems and stats, we can apply thinking like this and ask, number one, does this fit the mathematical constraints? If I got negative 12%, something went horribly wrong. Or if I got 145%, something went pretty wrong as well. But I can also use reasonability constraints, like the one I just mentioned, right? Can I bound my answer within reasonable constraints and see if it fits that constraint? Any questions on this? Okay, let's discuss conditional probability just a little bit further. So if we look at our multiplication rule for dependent events, let me box it over here. We see this conditional probability comes up, this probability of B given A. I can solve for probability of B given A by dividing both sides of probability of A, presuming that probability of A is non-zero. If probability of A is 0, A cannot occur, and then it's a little silly to ask, what about the event B, given that A has occurred? A can't occur, so it's a bit silly to ask anything about B. So if we presume probability of A is non-zero, so that this conditional probability kind of is a sensible question to ask, we can divide through by it. Probability of B given A is probability of A and B over probability of A. And I think this also contributes, this formula here also contributes to people wanting to treat this given bar, this vertical bar, like a divided by sign, which it really is not. So don't get, especially when we get to things like Bayes' theorem, thinking of it that way is really going to kind of mess things up. So this B given A here is its own notation, and it's related to a ratio. It's related to a fraction, probability of A and B over probability of A, but it's that vertical line is not a division line. That's one of the most common things, the most common error that I see in anything involving conditional probability is people take this and then make it probability of B divided by probability of A, and that's not what it is. Let's skip over this. This is just kind of an interesting little little argument here that things like coin flips, they have this memoryless property that if you kind of have succeeded a bit already, the probability kind of only looks forward. It doesn't really care about your past successes. It's only looking forward. We're going to skip that, though. That's kind of a minor point, just to make sure we can wrap up at least this slideshow before next time. Okay, so let's look at an example here. Let's suppose that the probability of parking in a no parking zone and getting a parking ticket is 6%. So I went to grad school at Pitt, and I was a commuter, so notoriously, it's pretty challenging to park in Oakland. So let's use that context. And let's say, if I look back over the last 100 days that I went to school, there were some of those days where I parked in a no parking zone and got a parking ticket, and maybe 6 of those 100 days that had occurred. So the probability of parking in a no parking zone and getting a parking ticket, I estimate to be 6%. Now, again, I look back over those 100 days and I ask, well, what's the probability that I park in a no parking zone? In other words, of those 100 days, how many times did I park in a no parking zone? Maybe that was 20 of those days. So I estimate the probability that I can't find a space and need to park in a no parking zone as 20%. And my question is, so I leave my house today, I get to campus, I see, oh, there's some crazy event going on. I can't find anywhere to park. I need to park in a no parking zone. Given that I parked in a no parking zone, what's the probability I'll get a ticket? Given that I have this kind of extra piece of information. When I left my house this morning, I expected the chance that I would park in a no parking zone and get a ticket at 6%. But I get to campus and I see the parking situation is really bad today, in a sense, what's my updated probability of getting a ticket given that I know that I parked in a no parking zone? It won't happen all the time, but I think we can intuitively expect that it's going to go up. It's got to be more than 6%. So let's call the event N parking in a no parking zone, and the event T is getting a ticket. So probability of T given N, what's the probability I get a ticket given I parked in a no parking zone today? Well, just by our conditional probability formula, that's probability of T and N over probability of N. Right, because probability of T and N would be probability of N times probability of T given N, just rearranging that. What's the probability that I park in a no parking zone and get a ticket? That was 6%, so that's 0.06. What's the probability I park in a no parking zone in general, whether or not I got a ticket? That's 20%, 0.2. 0.06 over 0.2 is 0.3 or 30%. So given that when I left the house this morning, I estimated there would be a 6% chance that I would have to park in a parking zone and get a ticket. But now, given that I got to campus, parking situation's bad, I know that I parked in a no parking zone, my probability of getting a ticket has increased fivefold. Or dividing by 0.2, that's multiplying by 5. It's increased fivefold to 30%. I now have a 30% expectation of getting a ticket today, given that I parked in a no parking zone. Any questions on any of this? Okay, and here's another kind of like side example. Um, I I'm not really going to go through this because I think it'll take more than 7 minutes, and it's just, you know, sometimes when we have time, I go through it. But really, the crux of the idea here is that pharmaceutical trials are complicated, and the successes need to pay for the failures. And if we were to look at a scenario like this, these are reasonably accurate numbers from about 10 years ago. It's actually really hard to find these numbers and getting more challenging. So I dug into this quite a bit about 10 years ago and found all these numbers and inferred some others. But the successes need to pay for the failures. And, most of the ideas end up being failures. So that is kind of what we're looking at here. And you can see the famous tree diagram popping up to kind of help us work through this problem. But again, this is kind of a side note. Are there any questions on anything we talked about today? Don't see anything in chat. All right, we'll end a few minutes early today. Let me stop the recording.